Hello class, this is CSE-4600, section 62, week 6, so technically it's week 7 now. Fall 2024. So this is hopefully going to be the last part of chapter 2 we're going to look at. So, chapter 2 was a big, hefty chapter, but the next chapter, if you look at the syllabus, it's supposed to be that chapter 3 is next, but I want to follow along closely with the other operating systems book as closely as possible. That's why the next chapter is not going to be on memory, but rather on deadlock. So our next chapter is actually going to be chapter 6, so we're going to hop around chapters a little bit. So, we had left off our discussion on CPU scheduling. So, really there are about 4 important CPU scheduling algorithms that you should know. And I've highlighted them here. So, really, I feel like it's better if we have a few examples that we can work with for scheduling, CPU scheduling. So, as I said, the 4 important ones that you probably need to know are first come, first served, shortest job first, round robin, and priority scheduling. So, let me take it from the current slide. Now, first come, first serve is the simplest non-preemptive scheduling algorithm. Non-preemptive meaning, once the CPU is allocated to a process, it does not let go of it until that process is done. Any other process that's in the queue waiting for the CPU, it's gotta wait their turn. The advantage of first come, first serve is that it's easy to understand and easy to implement. The disadvantage is that waiting time. Because first come, first serve is non-preemptive, that process is gonna be using the CPU. That CPU is gonna be allocated to the process, even if the process isn't doing any work, even if it's waiting for an I/O operation. So the smart thing to do would be if that CPU is waiting for an I/O operation to finish, that means the CPU is not doing anything. That would be a good opportunity to preempt the CPU so that another process can run. But we are not working with preemptive scheduling systems right now. The point is this. If a process is doing a lot of I/O bound work, then it would be considered unfair for any processes that are waiting in line. So, what if we knew ahead of time how long each process is going to run? To minimize the waiting time, what we could do instead is have it so that the shortest process, the process that we know is going to run for the shortest amount of time, is run first. And then the next process after that with the second shortest runtime. And so on and so forth. That is the basis behind shortest job first, or SJF. The advantage of this is that it is optimal. And there's a way we can prove it that it is optimal, that we can get the lowest waiting times possible. However, it's not emphasized in this book. It is emphasized in the other operating systems book because we need to know this information ahead of time, how long processes are going to run. We can't implement SJF in practice because we cannot know how long these jobs will run for. We need a crystal ball for that, and crystal balls in computer science are reserved for thought experiments. There's something similar called shortest remaining time next. But again, we need to know this information in advance. Okay, so now we're going to look at round robin and priority scheduling. Round robin is one of the simplest, fairest, and widely used scheduling algorithms right out there. Simply put, processes take turns running the CPU. They'll use the CPU for some amount of time called a quantum, and once that time is up, the CPU is preempted and given to another process. This makes round robin the first preemptive scheduling algorithm that we're looking at. So, a process is allocated the CPU for some amount of time, say 100 microseconds. No, maybe 100 milliseconds. During that time, it's going to use the CPU. If time is up, if the 100 milliseconds is up, it's time for the next process to run. If, before that time, that process can't run anymore because it's waiting for some I/O operation to finish, well, that means we can give the CPU to the next process earlier. So let's say at 50 milliseconds, the process stops running because it's waiting for some I/O operation to finish. At that point, we can preempt the CPU. That process goes back to the line, to the back of the line. And then we can give that CPU to the next process in line. The one variable about how round robin works is how long to make that quantum. Due to the overhead related to context switching, a large quantum is recommended so we don't waste too much time on context switching. However, a small quantum is recommended to make sure that an interactive system is responsive. And if the quantum is way too big, then round robin devolves into first come first serve. So really, what we gotta do is find a good sized quantum that balances context switching and responsiveness. In practice, it's something like 20 to 15 milliseconds. So let's get to priority scheduling. Round robin makes the implicit assumption that processes are equally important. This isn't always the case. You might have some process that's more important that needs system resources more urgently than other processes. This is a common thing with operating systems. So we say that these processes are higher priority. In priority scheduling, each process has a priority level. Whichever process has a higher priority is the one that runs first. Here's a question. Is it smaller values or larger values that are high priority? Oh, the problem with that is that the rules for that are inconsistent. So, for some systems, it might be smaller values is higher priority. In other systems, it might be larger values as higher priority. It's not really specified. There's no standard for priority levels, so we just go with whatever standard the system has being enforced. If a process has a higher priority than other processes in the queue, so this is what priority scheduling does. If a process, let's say we have a queue full of processes waiting for their turn on the CPU. A higher priority process comes in. It has a higher priority than all other processes in the queue. It goes to the front of the line. And we can do this using what's called a priority queue. This is a data structure we can use to implement priority scheduling. If the scheduling algorithm is preemptive and the process at the front of the queue has a higher priority than the currently running process, then that currently running process is removed from the CPU. The CPU is preempted to the next process in line, which is the high priority process. That way, the high priority process can run first because, well, of course, it's high priority. So here is where we get to see a few examples of this. So this is the one thing that I did not get to do in the last set of slides. I want to show you a few examples of this. So suppose we have 4 processes queued up for the CPU, and they all arrived in the following order before any process was able to run. So process 1 arrives, and we know it's going to run for 8 milliseconds. Process 2 arrives, and we know it's going to run for 3 milliseconds. Process 3 arrives after that, and we know it's going to run for 15 milliseconds. Process 4 arrives after that, and we know it's going to run for 5 milliseconds. Using first come, first serve, we basically run these in the order in which they arrived. That is, process runs first for 8 milliseconds, process 2 runs second for 3 milliseconds, process 3 runs third for 15 milliseconds, and process 4 runs fourth for 5 milliseconds. One thing to consider is how long each process is waiting for the CPU. So, for the processes in the queue, they are waiting for their turn on the CPU. Because in this example it's first come, first served. Well, process 1 doesn't wait at all. It's the first in line, so it runs first. Process 1 waits for 0 milliseconds because it was the first to run. Process 2 must then wait for process 1 to finish. So it's going to be waiting for 8 milliseconds. Process 3 waits for process 1 and 2. So that's going to be a total of 11 milliseconds. Process 4 must wait for all processes before it to finish. So it's going to wait for process 1, and then process 2, and then process 3. That's a total of, well, if you add these values up, that is 26 milliseconds of waiting time. And if we average that out, our average waiting time is 11.25 milliseconds. Which doesn't sound like a lot in the context of processes, but, well, in the context of our time scales, because 1 millisecond is 1/1000th of a second, doesn't sound like a lot of time, but for processes, this could be considered a lot of time. Let's compare that to shortest job first. So we're going to order these processes by how long they're going to run. And we know how long they're going to run. So we're going to reorder the processes based on increasing burst time. Process 2 now runs first because it's going to run for 3 milliseconds. And then process 4, which is going to run for 5 milliseconds. And then process 1, which runs for 8 milliseconds. And then finally process 3, which runs for 15 milliseconds. So now, processes are going to wait, but the idea is they're going to wait for less time. Process 2 waits for 0 milliseconds because it was the first to go. Process 4 now must wait for process 2 to finish, which is going to be 3 milliseconds. Process 1 must wait for the processes 2 and 4 to finish, and that's going to be an 8 millisecond waiting time. And then finally, process 3 must wait for all other processes before it to finish. So process 2 runs for 3 milliseconds. And then process 4 has to run for 5 milliseconds. And then process 1 runs for 8 milliseconds. This totals up to 16 milliseconds of waiting time for process 3. That's the last process. So, if we average that, we get 6.75 milliseconds, which is far lower than with first come, first serve. We can draw all this out using something called a Gantt chart. We use this to visualize how long these processes are running for. So with first come, first serve, process 1 runs for 8 milliseconds, and then process 2 for 3 milliseconds, then process 3 for 15 milliseconds, and then process 4 for 5 milliseconds. And I also color-coded these. If there is a bit of a risk of having color-coded anything, but because, well, color blindness and all, but hopefully it should be clear that these things are different sizes. I mean, they have labels and all, so, you know. SJF is where we order these processes in increasing burst times. So process 2 runs first because it has the shortest burst time of 3 milliseconds, then process 4, then process 1, and then process 3. The end result is that we arranged these processes in different orders, resulting in different wait times, resulting in different average wait times for these processes. So let's look at an example of round robin. So we're gonna do 2 examples of round robin and the difference is how long that quantum is. To use round robin, we need to decide on how long that quantum is. Let's do 3 milliseconds first. As before, processes run in the order they were added to the queue, but they will only run for 3 milliseconds at a time. the Gantt chart becomes a bit more complex, as thus calculating waiting times. So, we have these run in the order they were placed in the queue. So process 1 runs first, but it only runs for 3 milliseconds at a time. Once that time is up, the CPU is preempted, and then process 1 goes to the back of the line. Now it's process 2's turn to run. It runs for 3 milliseconds, but oh wait, didn't we establish that process 2 runs for 3 milliseconds? Well, once that's done, process 2 will not run again because it's done running. So, process 2 will run for its entire quantum, and then it's not going to run again. So it doesn't get placed back in the queue anymore. It's done. The process terminates. So now it's process 3's turn to run. So it runs for 3 milliseconds. Once that 3 milliseconds is up, it's process 4's turn to run, and it runs for 3 milliseconds. Okay, so as that happens, processes are moving from the back of the line to the front. Now it's process 1's turn to run again. So it runs for 3 milliseconds again. And then process 3 runs for 3 milliseconds after that, because process 2 doesn't need to run anymore. It terminated already. So now it's process 4's turn to run, but hey, look, process 4 runs for 5 milliseconds. So what happens is this. It's going to run for 2 milliseconds, but when it does, it terminates. So now we can preempt the CPU early. So now it's process 1's turn to run. But it terminates early because it didn't use up, in either case, it didn't use up its full quantum. When a process stops running before the quantum is up, we can just preempt the CPU earlier. So so the second time that process 4 runs, it only ran for 2 milliseconds, and then it was done working. We can just preempt the CPU earlier so that the next process in line can run. Process 1 is much the same. It runs for 2 milliseconds because it finished its job before the quantum was up. Now it's process 3's turn to run. At that point, process 2 has terminated, process 1 has terminated, and process 4 has terminated. So that's 3 processes, and that means process 3 has the whole CPU to itself. So it's gonna run and run and run until it's done. So here's where that waiting time calculation becomes a little bit trickier. So process 1 runs first for 3 milliseconds. After the 3 millisecond mark, it must wait for process 2, 3, and 4 to finish their turn on the CPU before it gets to run again. So that's 9 milliseconds of waiting time, just for the second time it runs. And then process 1 runs for another 3 milliseconds until it's taken out from the CPU and goes back in the line. There it has to wait for 5 milliseconds for it to run again. So that's 9 and 5 milliseconds of waiting time. Process 2 must wait for process 1 to finish. It waits for 3 milliseconds. But process 2 has a burst time of 3 milliseconds, so it's only going to run for 3 milliseconds, and then it's done. So it only had to wait for 3 milliseconds. Process 3 must wait for processes 1 and 2 before it can run. So that is 6 milliseconds of waiting time just to run for the first time. For the second time, it must wait for... No, that is 6 milliseconds of waiting time. For the second time, that is also another 6 milliseconds of waiting time, because it has to wait for processes 4 and 1. The third time it waits, it has to wait for 4 milliseconds because P4 and P1, they finished early. And after that, process 3 can just keep on running and running and running uninterrupted. So that is 6, 6, and 4 milliseconds of waiting time. And then process 4 runs twice. So the first time, it runs for 3 milliseconds after it has waited for 9 milliseconds. And then it goes back to the line, and then it has to wait for another 6 milliseconds after that. And then it gets to run for the second time. If we add up all those waiting times, process 1 waited for 12 milliseconds because the first time it ran, it waited for 0 milliseconds. The second time it ran, it waited for 369. Process 1 waited for 12 milliseconds. I'm not sure if that value is correct, but yeah. Process 2 waited for 3 milliseconds. Process 3 waited for 16 milliseconds because I had to wait for process 1 and 2 to run the first time, process 4 and 1 to run the second time, and then process 4 and 1 again to wait the third time, and then successive times after that it doesn't have to wait at all because it's the only process left in the queue. Process 4 had to wait for 15 milliseconds, so I had to wait for 9 milliseconds the first time, and then 6 milliseconds the second time, so a total of 15 milliseconds. The point is, we have now a different average waiting time that is not as good as shortest job first, and slightly worse than first come first serve. So remember, the one thing we can do regarding round robin is we can change that quantum. Let's see how changing the quantum from 3 milliseconds to a different amount would affect waiting time. So we're gonna do this all over again with a quantum of 1 millisecond. Now the Gantt chart looks like this. It's even more chopped up. So process 1 waits for 0, 3, 2, 1, and 1 milliseconds to run. Process 2 waits for 1, 3 milliseconds to run. Process 3 waits for 2, 2, 1, and 1 milliseconds to run. Process 4 waits for 3, 2, and 2 milliseconds to run. And if we did all the work, we have total wait times of 15, 7, 16, and 13 milliseconds. That averages out to a waiting time of 12.75 milliseconds. So still not as good as SJF. And here are all the Gantt charts so far, comparing all their different runtimes. So now, let's talk about preemptive priority scheduling. Suppose we have the same 4 processes as before, but we have a 5th process, arriving at time 5 with a higher priority than all other processes. So process 1 has a burst time of 8 milliseconds. Process 2 has a burst time of 3 milliseconds. Process 3 arrives with a burst time of 15 milliseconds. Process 4 is 5 milliseconds. They all arrived in that order at the same time. But at time 5, process 5 arrives with a 4 millisecond burst time with a high priority. There are two varieties of priority scheduling. The first one is non-preemptive. The CPU is kept by the currently running process until it stops running. And then we have preemptive. The CPU is preempted and given to the high priority process. As far as the high priority process is concerned, preemption affects how soon it's able to run. The simplest way to implement priority scheduling is as a variant of first come first serve. When a high priority process is added to the queue, it's brought to the front of the queue instead. So here are the Gantt charts for that. So when process 5 arrives with a higher priority than all other processes, with non-preemptive scheduling, it simply waits for process 1 to finish its job. And then process 1 is done, it's process 5's turn. Because process 5 has a higher priority than all the other processes, it gets to run first before processes 2, 3, or 4. And that's with non-preemptive scheduling. What's preemptive scheduling? Process 1. When process 5 arrives, process 1 is preempted, and then it moves to the back of the line. And then process 5 can run. And then process 2 after that, and then process 3 after that, and then process 4 after that, and then process 1 after that. Scheduling in interactive systems. Okay, so there is another issue with priority scheduling. And I guess I don't have room to show all of this. So there is a few issues regarding priority scheduling. And one of them is called starvation. If we have multiple high priority processes entering the queue all the time, then there is a risk that low priority processes may not be able to run at all. One solution to this is called aging. So this means we increase the priority level of low priority processes over time, so that way, eventually, the priority of these low priority processes will be so high that it will be the next to run. Also keep in mind, it's also possible to integrate priority scheduling into round robin. In that case, if a high priority process enters a queue for round robin scheduling, the CPU is preempted and given to the high priority process until it finishes running. So this isn't in the book, so it's taken from the OS book from the Silver Shots OS book instead. With priority scheduling, there may be one queue for all priority levels, which, as I said, might run the risk of starvation for lower priority processes, unless we have a policy that increases priority levels of low priority processes over time. In some cases, particularly regarding how long it takes to search for the highest priority process, it's easier to have separate queues for different priority levels. That's what it means to have multiple queues. Each queue is for a different priority level. Okay, so shortest process next. Let's look at the next one. This one was a little bit incomplete. I'll have to fill that in later. Okay, guaranteed scheduling is based on a promise. Given n processes on a system, each process is guaranteed to get 1 over n of the CPU time. This requires keeping track of how much CPU time each process has had since its creation. For example, if a process has existed for 2000 milliseconds and it's one of 5 processes in the system, then 400 milliseconds of its existence should be CPU time. If this process had only ran on the CPU for 100 milliseconds, then it's entitled to more CPU time. However, if it ran for 800 milliseconds, then it has had more CPU time than it was entitled to. An algorithm chooses which process has the lowest ratio of actual time to entitled time as the next process to run. So if this process was entitled to 400 milliseconds of CPU time, but it only had 100 milliseconds, it might be the next to run. However, if that process had 800 milliseconds when it was only entitled to 400 milliseconds of runtime, then it might not be run for some time. Lottery scheduling is like guaranteed scheduling in terms of results, but has a much simpler implementation. Each process gets a lottery ticket for the CPU. Periodically, the system holds a lottery and each winner gets to run the CPU. Processes may get extra tickets to increase their chance of winning. Cooperating processes may exchange tickets with one another. Generally, whichever process has the most tickets has the highest chance of winning and thus has the highest share of CPU time. Also, we can apply lottery scheduling to other system resources, not just the CPU. Fair share scheduling is based on how many processes each user is creating. If user 1 creates 9 processes and user 2 creates 1 process, then user 1 has 90% of the CPU utilization and user 2 only has 10%. Fair for the processes, but not necessarily fair for the users. What if user 2's single process was CPU bound? And what if user 1's processes did very little work? To make things fair, the system accounts for the number of users and gives each user the same amount of CPU utilization. For n users, each user gets 1 over n of the CPU time, regardless of how many processes each user makes. However, this can introduce the reverse problem. What if all of user 1's processes were all CPU bound and they were all working together to solve one problem? Then that wouldn't be fair to user 1. Let's backtrack. If user 1 creates 9 processes and user 2 creates 1 process, then user 1 has 90% of the CPU utilization and user 2 has only 10% of the CPU utilization. This is fair for the processes, but not for the users, because what if user 2's single process was CPU bound and needed more CPU time? Then that would not be fair. If, conversely, user 1's processes were all CPU bound and they were working together to solve one problem, then that wouldn't be fair to user 1. Really, the thing about this fair share scheduling, it depends on what counts as fair, so we can implement different policies based on what constitutes as fair. Okay, let's talk about thread scheduling. If a process is multi-threaded, how threads are scheduled depends on whether user threads or kernel level threads or both are supported by the system. And here we go with PowerPoint seeing thread and thinking thread as in sewing. With user level threads, the kernel is unaware of the existence of threads. Threads, what's that? I guess PowerPoint is unaware about the existence of threads in the context of programming. Anyway, the scheduling algorithm selects a process to run for some quantum. Within this process, there is a thread scheduler that selects a thread to run. It selects a thread to run until either the quantum is up or no more threads can run, whichever comes first. If the quantum expires while the selected thread was still running, the process with its current thread is preempted. When that process runs again, that thread runs again. If the selected thread finishes before the quantum expires, that thread scheduler will simply pick out another thread to run. If multiple threads within one process run for short bursts within the quantum, they'll take turns based on whatever scheduling algorithm that thread scheduler is using until the quantum for the whole process is up. We can use any scheduling algorithm for our thread scheduler, but it's usually either round robin or priority scheduling. With kernel level threads, the kernel selects a thread to run, regardless of what process it was part of. This can pose a problem in that if we have thread 1 of process 1 running, and then it's time for thread 2 to run. Okay, let me back up. If we have, on the level of user level threads, we could have thread 1 of process 1, of process A run, and then thread 2 of process A running, and then thread 3 of process A running, and then we can have those alternate between one another. What cannot happen is thread 1 of process A running followed by thread 1 of process B running. That cannot happen under user level threads, but it can happen with kernel level threads. So what could happen is threads 1, 2, and 3 of process A run after one another, but what could also happen is thread 1 of process A can run, followed by thread 1 of process B, and then thread 1, and then thread 2 of process A, followed by thread 2 of process B. This poses a problem because the context switch threads requires less work than the context switch entire processes. What happens is this. If we are context switching threads in this order, we are basically context switching entire processes. If we are context switching threads in this order, then we have one big context switch for the entirety of process A. And then we have smaller context switches after that until all the threads of process A cannot run anymore, or the quantum for or the okay. Let me back up. If we have this ordering, then we have entire full context switches for each thread. If we have this ordering, then those threads have smaller context switches up until none of the threads of process A can run anymore. Then it's time for process B. Give me a minute. Yeah, so the major difference between kernel level and user level thread scheduling is performance. With user level threads, full context switching is only done on processes. Context switching threads that are part of the same process does not require as much work as context switching processes. With kernel level threads, since it's possible for threads of different processes to switch, you'll need a full context switch, which is expensive. What would be smarter is if the kernel knew that the next thread is going to be part of this previous process, it will not do a full context switch. If the kernel knew that the next thread is going to be a thread from the previous process, we do not need a full context switch. If the kernel knew that the next thread is going to be part of a different process, then yeah, it will need the full context switch. Finally, we get into two final things. Classic interprocess communication problems. This is the final part of the chapter we're going to look at until we get... this is going to be the last part of the chapter, and then we can talk about the next chapter. The first one is the dining philosopher's problem. So Edgar Dijkstra, yes, that Dijkstra, posed a thought experiment that he called the dining philosopher's problem. So imagine 5 philosophers sitting at a table, each with a plate of food in front of each philosopher, with one fork set between each plate. Each philosopher is in one of 2 states. They're either eating or thinking. To eat, a philosopher requires 2 forks. One on the left and one on the right. Oh yeah, and philosophers don't talk to one another, and they cannot take forks from one another. Different retellings of this may use chopsticks because it's kind of silly to use 2 forks to eat spaghetti. Also, it kind of makes sense to use chopsticks because you need 2 chopsticks to eat. You can't just use one. Regardless, the challenge is to write a program in which philosophers don't starve. Starvation, not only in the sense that they're deadlocked forever, but in the sense that they can die of actual starvation. So we might have code that looks like this. If a philosopher wishes to eat, the philosopher must call take fork on each fork or chopstick, one at a time. Once a philosopher is done, that philosopher must call put fork on each fork. So we can enumerate the 5 philosophers from 0 to 4. 0, 1, 2, 3, 4. So we have philosophers 0, 1, 2, 3, 4. And then we can enumerate the forks. So we have forks 0, 1, 2, 3, 4. If philosopher I wants to eat, that philosopher must acquire fork I and fork I plus 1 mod 5. That means if philosopher 0 wants to eat, that philosopher must acquire forks 0 and 1. If philosopher 4 wants to eat, that philosopher must acquire forks 4 and 5. There's no fork 5 because according to a lot modular arithmetic, if we go to number 5, that's basically the same as fork 0. So basically it's a way of saying take the left fork and the right fork, but these numbers are arranged in a circle. So the problem with this implementation is what happens if all 5 philosophers decided to eat at the same time? They'll grab their left forks, but they can't grab their right forks because it's taken by another philosopher. We end up with deadlock, and then all 5 philosophers starve to death. Yes, there is a small chance of this happening, but that's the problem. We want to keep this from happening, regardless of how unlikely it is. We need a better solution to this. So here's a much more involved solution that involves semaphores being introduced. We also need an extra state for all of our philosophers. We need an extra state called hungry. So now philosophers must be in one of three states. They're either thinking, they're either eating, or they're either hungry. We also need a mutex to control access to these critical sections. And then we need an array of states to use to keep track of each philosopher's state. So as I said, a philosopher is either thinking, is either hungry, or is either eating. When philosopher I calls take forks, down is called before entering the critical section. Once in, the philosopher changes their state to hungry and tests whether the forks can be acquired. After testing, the philosopher calls up to release the mutex. When a philosopher calls down on its own semaphore, if the forks were not available, then it will block itself until the forks become available. So I guess this is the only way that the philosophers can talk to one another, though it's more indirect. It's more for signaling, hey, it's your turn to eat now. Once a philosopher returns from calling take forks, yum yum spaghetti, the philosopher can eat. Yeah, it literally says yum yum spaghetti as a comment. Once a philosopher is done eating, they call, put forks to return the forks. This requires calling down to acquire the mutex before entering another critical section. Once in, the philosopher changes their state back to thinking. Then the philosopher calls test on the two forks to see whether there were any philosophers who were blocked because they didn't have the forks. After leaving the critical section, the philosopher calls up on the mutex to release the lock. Yeah, it sounds a bit more involved, but that's because we want to keep deadlock from happening. And chapter 6 is all about deadlock. We don't want deadlock to happen. We don't want starvation to happen. So all this is necessary to keep the potential danger of starvation from happening. Okay, so the next problem is called the reader's-writer's problem. The dining philosopher's problem models processes accessing a limited resource, whereas the reader's-writer's problem models access to a single shared resource. So we have processes that are reading and writing to some database, and there's one big database. Here's what's going on. There are multiple processes that are either reading from a database or writing to a database. There is no problem with multiple processes reading from the same database. However, if a process needs to write to that database, it must have exclusive access to that database. So no one is allowed to read from that database, and no one else is allowed to write either. So here's one possible solution to the reader's-writer's problem. The first reader to enter the database calls down on the mutex, and the last reader to leave the database calls up on the mutex. Again, there's no problem with having multiple readers in the database. If a writer wants to make changes, it may not be admitted if the mutex is locked. In that case, it's suspended until the mutex is released. So if there are 3 readers in the database and a writer wants to write something to the database, it's not allowed in until all the readers have left. This could be a problem if readers are constantly entering the database. However, we might be able to fix it so this works instead. Say there are 3 readers currently in the database, and a writer says, I need to write something into that database. So, when it tries to enter the critical section, what it will do is this. When that writer says, I need to write something to the database, any other processes that were trying to enter the database, say there's a 4th process that wants to read from the database, it's blocked. So now, processes that want to enter the database when a reader processes that want to read from the database, when a process wants to write to that database, it now has it set up so it basically has a closed sign in front of the database. Any processes that are still in the database are free to read until they leave. Once that last process has left, the writer is now free to enter the database. Once that writer is done, it's going to take out that closed sign so that any processes that were blocked from entering can now re-enter the database. I guess a real life example of this is when you have a cleaner who's trying to clean a bathroom. They'll put up a closed for cleaning sign. Anyone who's still in there will just do their business and then leave after that. And that is the end of Chapter 4. I would like to give you your next lab assignment, but I have not gotten around to doing that just yet, so I might just give you a filler assignment where you do, for example, process scheduling, CPU scheduling for processes, and compare their wait times and all. This will require you to draw a few Gantt charts, by the way. So, with that, let's get to our next part, and that is Chapter 6. This is where things get serious, by the way. Oops. Let's open up that slideshow. So now we are in Chapter 6. As I said, I wanted to do Chapter 3 next, but I think it's more appropriate if we go into deadlock before we get the memory. Okay, so computer systems are full of resources that can only be used by one process at a time. Also, some processes may need access to multiple resources. If a process, however, tries to get something that another process already has, but that process has something that the first process already has, then these processes block one another and they can't work. We get deadlock. You see this mess over here? So this is an example of what's called gridlock. This is deadlock on the level of busy intersections. So these cars are trying to move forward, but they're blocked because these cars are trying to move forward, but they're blocked because these cars are trying to move forward, but they're blocked because these cars are trying to move forward, because they're blocked because these cars are trying to move forward, and it's a loop. That's actually one of the conditions for deadlock. We'll get to that in a little bit. The things that a computer needs... Okay, this one also needs some corrections. The things that a process needs access to includes devices, data records, files, the CPU, all sorts of things. We'll call these resources. Resources are anything that must be acquired, used, and released over time. Resources can be a hardware device or a piece of information, such as a record in a database. In some cases, there can be multiple instances of the same resource. Let me fix this right now. Yeah, and then I'll do my best to update these slides as well. Resources come in two types. They're either preemptible or they're non-preemptible. And we've seen one example of a preemptible resource, the CPU. When a process runs for some amount of time, but it finishes its job before that, or it's blocked and has to wait for I/O, then the CPU can be preempted and then given to the next process in line. Basically what happens is, with a preemptible resource, they can be taken away from a process without any ill effect. Non-preemptible resources cannot be taken away without potentially causing failure, such as access to a shared file. One such example of a preemptible resource is, of course, the CPU. We can preempt it from a process, but that would require a context switch to make sure that the state of that process is saved, so that when that process runs again, we can just reload its previous state, so it'll just start again where it had left off. And processes are okay with that because we have the means of doing a context switch. Another example is memory. So we did not get to this just yet, but in most computer systems, when a program is loaded, we don't load the whole program. Rather, we load only the parts that are needed because the program itself is broken up into what are called pages. So we just load the pages into memory as needed. And if we don't need those pages to be loaded from memory, we unload them from memory. If a process needs more memory and it needs to take it away from other processes, then what will happen is those pages are unloaded and those freed up, and that freed up space can be used for other processes. That's an oversimplified version of what goes on in memory, by the way. But the base idea is a program is broken up into pages, and pages are loaded into memory as needed, or they can be unloaded from memory as needed. And that's how memory is a preemptible resource. And again, this does not hurt the program in any way, except it might hurt for performance. But the point is, it does not hurt the process in a way that would destroy it, that would mess up its execution. Generally, deadlocks occur with non-preemptible resources. Because if a deadlock happens with a preemptible resource, all we gotta do is reallocate resources so that whichever process needed it more will use that resource. And then once that's done, that resource is free to be used by another process. Say a video game requires like a lot of memory, and by a lot of memory, I mean this much memory. I guess I've been using this thing for so long that okay, it's probably because I turned off my virtual machine. I was previously recording a 5250 video for this. So basically, resources such as memory, they can be redistributed to other processes as needed. Oh yeah, I have a game of Minecraft just paused in the background, and it is using up memory as well. Yeah, previously when I had my virtual machine up and running, it was using all 32 gigabytes of memory on my machine. And then it was using my hard drive as extra memory in a way. That is gonna be its own discussion later on, by the way. But yeah. Let's get back on track. Oh, and by the way, this screenshot was from that same instance of Minecraft. It's a mod pack, by the way. It's a mod pack in which your goal is to create an efficient factory. Which coincidentally means if you're gonna build a factory like this, you're gonna have a lot of the same concepts as with computer science in general. And then we have the conspiracy theory that says Factorio teaches you software engineering or something like that. Let's get back on track before I get distracted any further. My point is this. If we have preemptible resources, then we can't have deadlock happening because we can just reallocate resources as needed. Therefore, our discussion on deadlocks will be on non-preemptible resources. The use of a resource is done in 3 steps. Number 1, request a resource. If a resource is not available, then the process is blocked and awakened when it becomes available. Alternatively, that request returns with an error code, and it's up to the calling process to wait and try again later. That's number 1. Number 2, once it's acquired, use the resource. And once it's done being used, number 3, release that resource. When processes are unable to acquire a resource, we're just going to assume they're good asleep, and they are awakened when that resource becomes available. For some resources, no system calls are needed, so it's up to the processes themselves to manage these resources. We can do that by using semaphores. Calling down decrements the available resource by 1. If it was 0, then the calling process is blocked. Calling up increments that available resource by 1. If another process was blocked because there were no resources available, it is awakened, and basically, hey, it's your turn with the resource now. And this will work for any number of resource types. With 2 processes, things can change depending on the order in which these resources were acquired. Depending on how the code is written, we might get deadlock. With the code on the left, processes acquire resources in an order that prevents deadlock. So basically, process A acquires resource 1. If that resource runs out, process B will basically wait its turn until that resource becomes available. However, with the code on the right, what can happen is this. Process A first acquires resource 1, and then we're out of resource 1. Process B acquires resource 2, but now we're out of resource 1. So now, both processes are waiting on each other, and now, because neither process's requests are being fulfilled, they're blocked forever and they can't do work. We have deadlock. A set of processes is deadlock. This is the definition of deadlock. A set of processes is deadlock if each process in the set is waiting for an event that only another process in that set can cause. Because all processes are waiting and assumed to be sleeping, no processes can wake up one another. For our deadlock model, we're going to make a few assumptions. 1. Processes are single-threaded and no interrupts are possible to wake up a blocked process. Number 2. We're dealing with something called resource deadlock. There are other types of deadlock that we might look into later on, but we're going to look at resource deadlock. Deadlock can only occur if 4 conditions are met. Number 1, mutual exclusion. Resources are available or assigned to exactly one process. Put another way, one process can only use a resource at a time. Hold and wait. Processes currently holding resources that were granted earlier can request new resources. Basically, a process requests resources, and then that process requests for more resources. It will hold on to all the resources it has requested until all of its requests are fulfilled. No preemption. Resources given to a process can only be released by that holding process. And that's number 3. Number 4, circular wait. At least 2 processes are waiting for one another in a loop like this. I'll explain what this diagram is later on, by the way. We can eliminate deadlock by removing just one of these conditions. So we can eliminate mutual exclusion, or we can eliminate hold and wait, or we can eliminate that no preemption thing, or we can eliminate circular wait. We can eliminate, if we eliminate even just one of those, we don't have deadlock. We'll look into that later on, by the way. Which of these conditions can be negated? So let's talk about that drawing earlier, this one. So we can visualize deadlock by using a graph. So processes are circles, resources are squares. If a resource is allocated to a process, then a directed edge, basically an arrow, is drawn from the resource to that process. If a process is requesting a resource, then an arrow will be drawn going from that process to that resource. So this is resource allocation. A resource is allocated to a process. This is resource requesting. A process is requesting a resource. If that request is successful, then this arrow reverses, so it's not a request anymore, it's allocation. If we have a loop like this, if there are any loops in our deadlock graph, we have deadlock. So here's an example of how deadlock can happen. So, A requests R and it's successful. B requests S and it's successful. C requests T and it's successful. And then A requests S but has to wait for that because it's currently allocated to B. B requests T but has to wait for that because it's currently allocated to C. C requests R but has to wait for that because it's allocated to R, because R is allocated to A. look, we have a loop. And then where there's loops, we have deadlock. I just realized that camera is in the way. So yeah, here's the full graphs and how these requests lead to deadlock. Let's look at an alternative. Let's look at another ordering of this. Basically, we can order our requests in a way that prevents deadlock from happening. So, we can do this in a different order. A requests R and it's successful. C requests T and it's successful. Any request that B tries to make, we're going to ignore them for now. A requests S and it's successful. C requests R, but it's not successful because R is currently allocated to A. At some point, A is going to be done with resource R, and then resource R can be successfully allocated to process C. And the same is going to be true for resource S. So at some point, process A is going to be done with resource S and it's going to let go of it. If resource B needs any of these resources, then they're either going to be free up now, or they will be once process C is done with its resources. No deadlock. There are 4 general strategies to deal with deadlock. Number 1, ignore the problem and hope nothing bad happens. Number 2, let it happen, detect when it happens, and do something to recover from them. That's number 2. Number 3, carefully allocate resources in a way such that deadlock does not occur. Number 4, preventing it entirely by negating one of the 4 conditions for deadlock. Let's look at the first strategy. Ignore the problem. This is called the ostrich algorithm. Excuse me. So the ostrich algorithm is the simplest way of dealing with deadlock by simply not dealing with it at all. Much like how an ostrich sticks its head in the sand to avoid predation. Oh, and by the way, this is on the cover of the textbook. It's the ostrich algorithm. The front of the textbook is full of visual puns wrapped up in a carnival, and this is one of many visual puns. The problem with the ostrich algorithm is that it's based on a misconception that ostriches stick their heads in the sand to avoid predation. This is nonsense. Basically, ostriches can kick so hard that it can kill a lion. And even if it doesn't outright kill the lion, if the lion's jaw is broken by an ostrich's kick, then that lion will die of starvation because it can't eat anymore. So this thing about ostriches sticking their head in the sand, that's nonsense. What isn't nonsense is how sometimes the ostrich algorithm is acceptable. So the ostrich algorithm may be acceptable or unacceptable based on how often deadlocks happen. If deadlocks are so infrequent on a system, then why would you spend time and money to add a special system to deal with it? This depends on how frequent it is and how bad it gets. If it only happens like once in a blue moon, which means infrequently. If deadlocks happen once in a blue moon, say once a year, but the worst that can happen is that jobs take 10 hours more to complete, then why spend the money, time and money to implement a system to deal with a deadlock? If it's to the point where it would crash the whole system, then yeah, you would need to implement a deadlock mitigation strategy. So let's look at actual strategies to deal with deadlock. So we're gonna move away from the ostrich algorithm, which looks like a YouTube clickbait thumbnail now. Fact checked, false. Let's look at deadlock detection and recovery. The system does nothing to keep deadlock from happening. It does, however, detect whether it happens, and if it does, it takes some action to recover from it. So let's look at one example of this. Deadlock detection with one resource of each type. This is the simplest case of deadlock, where there's only one type of each resource. Let's consider an example with 7 processes and 6 resources. The question to ask is this: is this deadlocked? And if so, what processes are involved? So we have 7 processes. Process A is holding R and wants resource S. Process B is holding nothing, but it wants resource T. Process C holds nothing, but it wants resource S. Process D is holding resource U, but it also wants resources S and T. Process E holds T, but it wants V. Process F holds W, but it wants S. Process G holds V, and it wants U. Is this deadlocked? Well, to answer this question, we can just draw a graph of how these resources are allocated. To determine whether it is deadlocked, all I gotta do is find a cycle in the graph. So because all of these are directed edges, all we gotta do is find some loop in the graph. You see the loop? It's here. So process D wants resource T. Resource T is allocated to process E. Process E wants resource V. Resource V is allocated to process G. Process G wants resource U. Resource U is allocated to process D. It's a loop. We have deadlock. Although it's easy to draw the resource graph for some situations, and especially with larger descriptions, it's a good idea to have a formal description of the algorithm that we use to determine whether there is deadlock. So, for each node n in the graph, perform the following steps with n as the starting node. Initialize L to the empty list. Designate all arcs, those are arrows, as unmarked. Add the current node to the end of L, and check to see if the node now appears in L 2 times. If it does, the graph contains a cycle, and the algorithm terminates. That means we found deadlock. From that given node, see if there are any unmarked outgoing arcs. If so, go to step 5. If not, go to step 6. Pick an unmarked outgoing arc at random and mark it. Then follow it to the new current node and go to step 3. If the node is the initial node, the graph does not contain any cycles and the algorithm terminates. Otherwise, we have now reached a dead end. Remove it and go back to the previous node. That is the one that was current just before this one. Mark that one, the current node, and go to step 3. Yeah, it's a little bit complicated, but basically it looks like this. And I have it so that the ink. Hold on. Basically, what we're doing is if I go to a slide, I can do this thing where I can play the ink being drawn. So basically we're starting at some node and we are following the arrows until we can't follow them anymore. If we reach a point where there are multiple paths, we pick one path until we can't go any further. Then we backtrack and go down a different path. If we encounter the same node again, that means there's a cycle in the graph and we have deadlock. However, this isn't the whole graph, so there's more to this. So what we do is we start over at some other node that we haven't visited. So we're going to start over again. We're going to start at node B, and we're going to traverse this path, exploring every possible path until there's nothing else we can explore. Then we start over at a different node that we haven't visited yet. We keep going until we find a dead end or we find more deadlock. Once we find a node that we cannot traverse anymore, what we do is we simply backtrack to the previous node. If we keep backtracking until we find our starting node, that means there are no more paths that we can continue down. So we started node W. Our only path forward is to go to node F, and the only path forward after that is to go to node S. But there are no more paths, so we backtrack to F. But there are no more paths, so we backtrack to W. But there are no more paths, so that means we've explored everything that we can reach from node W. At that point, we keep going until we have explored every possible path if we found a node that we had visited earlier. So let's go back here. And replay this once again. We start at B, we go to T. And the only path forward is to E. And then the only path forward is to V. And then to G. And then to U. When you go to D, you have a choice to either go to S, which terminates. So we backtrack and go to T, which we had already visited. If we encounter a node that we had visited, we have deadlock. And that's how we determine that there is deadlock in the system. If we have multiples of resources, then things get a bit more complicated because now we have to keep track of things using matrices and vectors. So this is where it gets a little bit more complicated, but I'll do my best to explain what's going on here. We need a different approach for multiples of each resource type. So we have 4 things here. We have a vector for the resources in existence. We have a vector for the resources available. We have a matrix for all the resources that are currently allocated to each process. And then we have another matrix that says how much more of each resource each process needs still. The 2 vectors are the existing resource vector, denoted as E. This says how much of each resource exists. The second one is the available resource vector. This denotes how much of each resource has not yet been allocated to a process. This is vector A. Next are the 2 matrices. The current allocation matrix is a listing of how much of each resource is allocated to each process. Each row in this allocation matrix corresponds to how much of each resource is allocated to a process. We denote this whole matrix as C. The request matrix is a listing of how much more of each resource a process still needs. Each row represents a process's request for each resource type. We denote this whole matrix using R. Here's one property about these things. If we add up all the columns in C and add them to the corresponding values in A, we get the corresponding values in E. Basically, every resource is either available or allocated to a process. If we add these columns together and add them to their corresponding values in A, we get vector E. Deadlock detection is based on comparing vectors. This is a little bit tricky because this. Let's see this. Let's say we have some request here. We need to define an operation in which one vector is less than another. And it basically works like this. Say we have process 2 and has this request for resources. If R21 is less than A, R22 is if R21 is less than A1, and R22 is less than A2, and R23 is less than A3, and we keep going and so on and so forth, such that R2M is less than AM. If every value in this request vector is less than or equal to then the corresponding values in the resources available vector, then we can say that this request vector is less than the available resources vector. If that is the case, then that request, the whole entirety of it, can be fulfilled using the resources available. So here is the algorithm that we use to determine whether we have deadlock. All processes are initially unmarked. If a process is marked, then that process is able to complete its work and eventually release its resources. The algorithm is as follows. Look for an unmarked process Pi for which the ith row of R is less than or equal to A. If such a process is found, add the ith row of C to A, mark that process, and go back to step 1. If no such process exists, then the algorithm terminates. If the algorithm terminates with unmarked processes, then those processes are deadlocked. So we're gonna try a different example in the next video. So this is really the end of everything in here. I guess my next assignment for you is probably gonna be something involving CPU scheduling. I'd like for you to do something more with pthreads, but I think I'll have to save that for another time. For now, what I'd like you to do is, well, try this out, and then sometime later I'll give you an assignment where you try a few CPU scheduling algorithms by hand. I'm not going to have you write an algorithm. I'm not going to have you write a program for that. Rather, I'd like you to do this by hand because, well, it's a good idea to get these concepts down pat. So anyway, that's going to be it for now, and yeah, that's going to be it for now, and then we'll pick up with more on deadlock after that. So with that, thank you for watching, and I'll see you in the next video. Take care.